In this section, we define two new functions, but fortunately they're built out of functions that we recognize. We define the hyperbolic cosine, or the cosine, to be e to the t plus e to the minus t over 2, and the hyperbolic sine, or I just say it shine for short, is e to the t minus e to the minus t over 2. Now, let's just look at what those functions do. If we look at the cosine, as t gets large, this e to the minus t fades, and so this goes to 0, right? And so basically we're looking at e to the t over 2. On the other hand, if t goes to negative infinity, this one grows exponentially, or this one fades away, and it's e to the negative t that grows exponentially. So it's kind of like we have exponential growth two ways. Now notice when you plug in 0, you get e to the 0 plus e to the 0 makes 1 plus 1, that's 2. 2 over 2 is 1. So this function goes to the point 0, 1. It grows exponentially this way, and it grows exponentially that way. The shine, on the other hand, is just a little bit different. It goes through the point 0, 0, because if you put t 0 in for t, you get e to the 0 minus e to the 0. That would be 1 minus 1. That's 0 over 2, which is 0. So this one goes through 0. As t gets large, this part fades away, and so you just have exponential growth again. And as t goes to negative infinity, this one fades away, and now you have negative exponential growth. So it's got an arm that's bent down like this. So you could think about cosine is an even function, and shine, you can see, is an odd function. Just imagine what happens in shine if you replace t with negative t. You get the opposite of the function. Whereas here, if you replace t with negative t, these two just change roles, so you get the same function. So one's even, one's odd. When you add them together, you get e to the t. So some people say, well, cosine is the even part of e to the t, and shine is the odd part of e to the t. And that's interesting. So another reason why you'd want to look at these cosines is, or these hyperbolic functions, is because they're kind of common, especially in engineering problems. For example, you've probably seen a cosine today if you looked at power lines. So here's one power pole, and here's another power pole. It turns out the shape of this curve, it minimizes the potential energy for that wire. And so it assumes this shape sort of naturally, because that's the lowest energy configuration it can get into. And so if you look at the shape of power lines, those are based on the hyperbolic cosine. Some other things are hyperbolic cosines, like the Gateway Arch in St. Louis, I've heard is a hyperbolic cosine. So again, some energy principle that had to do with constructing that. So they're useful for lots of things. What we want to do is look at them. Now, there's a reason why they're called hyperbolic sine and hyperbolic cosine. It's because they have to do with hyperbolas. You're probably more familiar with ellipses. Here's a very basic ellipse. In fact, it's a circle, which is kind of a degenerate ellipse. Usually we think of an ellipse as an elongated circle. But this makes a circle of radius 1 here. If we write down kind of a companion equation, x squared minus y squared equals 1, then instead of getting an ellipse, what we get is a hyperbola. You can think the ellipse all fits inside a nice little box with sides of length 2 in this case, since it's a circle of radius 1. If you were to extend the diagonals of the box, so this line that goes through the opposite corner points, and extend these diagonals this way, then the graph of this equation, x squared minus y squared equals 1, would look like this. It would start here, and as x increases, and you'd see the y values, there's a plus 1 and a minus 1, and they straighten out to approach those straight lines. Oops. To start there, that's called the vertex of the hyperbola, and it moves backwards like this. So this is the basic equation of an ellipse, and sort of a very simple ellipse, right? A degenerate ellipse, in fact, because it's perfectly round, whereas most ellipses are kind of elongated. And this one is hyperbola. Kind of an interesting relationship there. In fact, they are both what we call conic sections. If I were to take a light bulb and put a shade, sort of a cylindrical shade around that light bulb, then you can see the shade will block the light or make it more diffuse. But where there's not a shade, you'll see a cone of bright light coming up and a cone of bright light going down. Let's just imagine that we have like an infinitely tiny shade, then we could create a cone that comes to a point. That would be a true cone there. So we have this cone of light. If you look at the pattern that the light makes on the ceiling, if you have a level ceiling, then the shape you'll see will be a circle of light, right? Where a flat plane cuts the cone, you get a circle. If your ceiling is maybe tilted a little bit, then you'll see an elongated circle, an ellipse, right? The circle is just a special case of that. If you tilt it even steeper, then you'll get a curve that doesn't close on itself. If you do it just right, you can get a parabola by doing that. But if you cut it with a plane that's steeper than the sides of the cone, then the plane will cut the cone. This would be like along a wall, right? The plane will cut the cone in the top and the bottom, and you get a shape that is in fact a hyperbola. So ellipses, parabolas, and hyperbolas are the shapes you can get when you cut a cone, and so they're called conic sections. Conic obviously for cone, and section for cutting. Okay, so now if you think about it, sine and cosine, the elliptic sine and cosine, are perfect for ellipses. If I let x be cosine t and y be sine t, then x squared plus y squared is cosine squared plus sine squared t, right, which would be 1. So if x and y just satisfy these two equations, then they parameterize a circle. They give me the 2 points x and y, my location in the plane, from one single point t. You might think of it as time. So if you watch these over time, they would just go around the circle. There's an identity that's similar for the hyperbolic sine and cosine. It's this. It's that the cosine squared minus the sine squared is equal to 1. So in that sense, the hyperbolic cosine and sine, if I make x be the hyperbolic cosine and y be the hyperbolic sine, then x squared minus y squared will automatically be equal to 1. So the hyperbolic sine and cosine are great for parameterizing hyperbolas, which are closely related to ellipses. That sort of explains why hyperbolic and why the similarity in the names. Let me just prove that identity, that cosine squared minus sine squared equals 1 for you. If you look at it, cosine squared minus sine squared, the definition of cosine is e to the t plus e to the minus t over 2. So this would be e to the t plus e to the minus t over 2 squared minus e to the t minus e to the minus t over 2 squared. So I'm just substituting in for cosine and sine, their definitions. If you don't learn anything from this video, it should be you learn that the definition of what the definition of cosine is and what the definition of sine is. Now, if you multiply that out, so we're multiplying a fraction times itself. We multiply the denominators. 2 times 2 will give me 4 in both cases. Now to do the tops, I have to use the FOIL method. If you take e to the t plus e to the minus t and multiply it by itself, the product of the first terms, e to the t times e to the t, would be e to the 2t. Right? So add exponents. E to the t times e to the negative t makes e to the 0, which is 1. You get 1 when you do the outside terms. You also get 1 when you do the inside terms, so you get 2. And then the last terms, e to the negative t times e to the negative t, if you add exponents, you get plus e to the negative 2t. On the other hand, if we had negative signs here, so if we're multiplying the top of sine times itself, we'd get e to the t times e to the t, we get e to the 2t again. But this time, when we take e to the t times negative e to the negative t, we get negative 1. And the same thing for the insides, we get another negative 1, so we have negative 2. And then the last terms, a negative times a negative is positive, we get plus e to the negative 2t. Both of these have the same denominator 4, so I can combine them. I've got e to the 2t plus 2 plus e to the negative 2t. And then I'm subtracting this whole numerator, so I'm subtracting e to the 2t. I'm subtracting negative 2, which would be the same as adding 2, and I'm subtracting e to the negative 2t. And notice that this negative e to the 2t cancels the positive e to the 2t. This negative e to the negative 2t cancels this e to the negative 2t. All that's left is 2 plus 2, so that's 4 up top and 4 down below. 4 over 4 is 1. So what we've shown is that sine and cosine satisfy this hyperbolic identity. Cosine squared t minus sine squared t equals 1. Okay, So those should be maybe the three things that you definitely learn from this section. The definition of the cosine is e to the t plus e to the negative t all over 2, and the definition of the sine is e to the t minus e to the minus t over 2. So, by the way, there's another connection between the hyperbolic sine and cosine and the usual sine and cosine, which you could also call the elliptic sine and cosine. You can define the cosine of an angle, if you don't mind using this imaginary number I, as e to the it plus e to the minus it over 2. See the similarity to cosine, except for you have an extra I up there. And you can define the sine as e to the it minus e to the minus it all over 2I. So if you don't mind using imaginary numbers, there's a definition for cosine and sine that are very, very similar to the definition of cosine and sine, right? The only difference is the addition of this I. I need to draw a little line here so you keep that 2 that's in the denominator of cosine out of the numerator of sine.